Hello everyone, and welcome back to our little community of dreamers and curious minds. Tonight, we're going to drift together through one of the universe's most mysterious and beautiful phenomena, black holes. I know what you might be thinking. Black holes sound intimidating, perhaps even frightening. But let me guide you gently into their world, where we'll discover not terror, but wonder. Where we'll find not chaos, but a kind of cosmic poetry written in gravity and light. Let me share something absolutely remarkable with you. Right now, as you settle into this moment, there are millions of black holes drifting silently through our galaxy. They aren't the destructive monsters of science fiction, but rather quiet sculptors of space and time, patient gardeners tending to the evolution of galaxies. They are, in their own way, the universe's greatest artists, painting with gravity across canvases billions of light years wide. If you enjoy these types of videos where we drift through the mysteries of the cosmos, uncovering secrets that will fill you with wonder as you relax, please take a moment to hit the like button and subscribe. It truly helps our community grow, bringing together more souls who find peace in the vastness of space. Now let your mind settle in, breathe slowly, and join me on this tranquil journey through the elegant darkness of black holes. Let's begin by gently correcting a beautiful misconception. Despite their name, black holes aren't holes in space. They're quite the opposite. They're the most substantial, most real objects in the entire universe. Imagine taking all the mass of a star many times larger than our sun and compressing it down into a space smaller than a city. The matter doesn't disappear. It becomes so incredibly dense that a teaspoon of it would weigh more than Mount Everest. This isn't emptiness. This is matter pressed into its most fundamental form, gravity made visible, existence concentrated into its purest expression. When you think of a black hole, think not of absence, but of presence so profound that space itself bends in reverence around it. Here's something that will make you pause and smile. Near a black hole, time itself becomes elastic, stretching like warm honey in sunlight. If you could somehow safely approach a black hole's edge, each second for you would become minutes, hours, or even years for someone watching from far away. You would age slower than the universe around you. It's not science fiction, it's Einstein's poetry, written in the language of curved space-time. Imagine floating there in that strange borderland where time softens and slows, where the frantic rush of the universe quiets to a gentle whisper. Near a black hole, you could exist in a bubble where minutes last lifetimes, where the chaos of the cosmos takes a long, deep breath. It's perhaps the ultimate sanctuary, a place where time itself surrenders to stillness. In our everyday world, nothing is truly perfect. Mountains have rough edges, planets bulge at their equators, even carefully polished ball bearings have microscopic imperfections. But black holes? They are nature's only perfect spheres. Their event horizons, those mysterious boundaries beyond which nothing escapes, form flawless mathematical circles in space, smoother than any surface humans have ever created or could ever create. This perfection emerges naturally from the laws of physics, from the symmetry of gravity itself. In a universe that seems to favor chaos and irregularity, black holes stand as monuments to geometric purity. They remind us that beneath the universe's apparent disorder lies an elegant mathematical grace. Picture a black hole in your mind now, a perfect dark sphere floating in space, as round as a thought, as smooth as silence. Let your worries drift away with this comforting thought. The nearest black hole to our Earth is about 1,000 light-years distant. To put this in perspective, if you traveled at the speed of light, the fastest possible speed in the universe, it would take you 1,000 years to reach it. At the speed of our fastest spacecraft, it would take tens of millions of years. This vast distance creates a cosmic buffer, a gentle cushion of space that keeps our world safe and serene. We live in a quiet neighborhood of the galaxy, far from these gravitational giants. When you look up at the night sky, you're seeing a peaceful realm where stars burn steadily and planets orbit calmly. The black holes are out there, yes, but they're distant lighthouses, not nearby storms. Sleep soundly knowing that Earth drifts through a tranquil region of space, where the nearest of these cosmic sculptors is separated from us by almost incomprehensible distances. Now let's drift into the realm of beautiful possibilities. Some of the most creative minds in physics have suggested that black holes might not be endings at all, but rather doorways. Deep within a black hole's heart, where our current understanding breaks down and quantum mechanics dances with gravity, there may exist passages to other universes entirely. These aren't just fanciful daydreams. They emerge from serious mathematical explorations of reality. Imagine, what appears as destruction on one side might be creation on another. The matter falling into a black hole in our universe might be emerging as the Big Bang of another cosmos, birthing new galaxies in dimensions we cannot perceive. It's a humbling thought, isn't it? That what seems like an ending might actually be a beginning, that destruction and creation might be two faces of the same cosmic coin. As you drift towards sleep tonight, picture the black holes not as cosmic graves, but as cosmic cradles, gently rocking new universes into being. Here's a secret the universe whispers. At the center of nearly every major galaxy, including our own Milky Way, there sits a supermassive black hole. These aren't stellar mass black holes formed from dying stars. These are monsters millions or billions of times more massive than our Sun. And yet, despite their enormous mass, they exist in a kind of gentle balance with their galaxies. They're not destroying their galactic homes but rather helping to shape them, regulate them, nurture them. The Milky Way's central black hole, Sagittarius A, pronounced A star, has a mass of about 4 million suns, yet it sits quietly at our galaxy's core, pulling stars into graceful orbits around it like a cosmic choreographer. These supermassive black holes may have been instrumental in galaxy formation, providing gravitational anchors around which stars could gather and dance. They're not invaders or destroyers. They're the ancient hearts of galaxies, beating in rhythm with billions of stars. In 2019, humanity achieved something remarkable and beautiful. For the first time, we captured an image of a black hole, or rather, its shadow. The Event Horizon Telescope, a network of radio observatories spanning the entire Earth, worked together to photograph the supermassive black hole at the center of the galaxy M87. What they revealed was breathtaking, a ring of glowing orange light surrounding a perfect circle of darkness. This wasn't an artist's interpretation or a computer simulation. This was an actual photograph, light that had traveled 55 million years to reach us, showing the silhouette of a black hole against the brilliant material swirling around it. That glowing ring you see in the image is matter heated to billions of degrees as it spirals toward the event horizon, its last light before disappearing forever. The image is both beautiful and humbling, proof that these mysterious objects are real, that they can be studied and understood, and that they possess an aesthetic grace that transcends their physics. Close your eyes and picture that luminous orange ring around the deepest black. It's one of the universe's most elegant portraits. Here's a gentle paradox for your drifting mind. Black holes, despite being the universe's most powerful gravitational traps, eventually evaporate. Stephen Hawking discovered that black holes emit faint radiation, now called Hawking radiation, due to quantum effects near their event horizons. This means they very, very slowly lose mass over time, like ice cubes melting in reverse, releasing energy back into the universe. But slowly doesn't begin to capture the timescale. A black hole with the mass of our Sun would take about 10 to the power of 67 years to evaporate completely. To put that in perspective, the universe is currently only about 13.8 billion years old, which is 10 to the power of 10 years. The evaporation of even a small black hole would take trillions upon trillions of times longer than the current age of the universe. It's a beautiful reminder that even the universe's most permanent-seeming features are temporary, that everything eventually returns to the cosmic ocean of energy. But there's no rush. These patient objects have time beyond measure, and their slow surrender to entropy is written in quantum whispers too faint to hear. Let this soothing truth wash over you. The universe has a rule that nothing is ever truly lost. When something falls into a black hole, it doesn't vanish into non-existence. Instead, its information, the quantum details of what it was, becomes encoded on the black hole's event horizon, like words written on the surface of a dark sphere. This is called the holographic principle, and it suggests that a three-dimensional object can be completely described by information stored on its two-dimensional boundary. So when matter falls in, it's not destroyed. It's transformed into a new form of existence, its essence preserved in the black hole's structure. Every particle, every atom, every piece of anything that ever fell into a black hole leaves its mark, changes the black hole slightly, adds to its story. In this way, black holes are the universe's memory banks, carefully preserving information even as they seem to hide it from view. Nothing is wasted in the cosmos. Everything becomes part of something new. In September 2015, humanity heard something no one had ever heard before: the sound of space-time itself rippling. Two black holes, each about 30 times the mass of the Sun, had been spiraling around each other for millions of years, drawing closer and closer. Finally, they collided and merged in a fraction of a second, creating gravitational waves, ripples in the fabric of space and time, that spread outward at the speed of light. When these waves reached Earth after traveling over 1 billion light-years, the LIGO detectors felt the tiny tremor, the faint echo of that distant cosmic collision. Scientists converted the signal into sound, and it's hauntingly beautiful. A rising chirp that climbs in pitch before ending abruptly as the two black holes become one. It sounds almost like a bird's call or a water droplet falling. This wasn't just a scientific achievement. It was the universe singing to us, sharing the music of gravity and time. Somewhere in the vast darkness, black holes are still dancing together, and occasionally, their final embrace sends ripples through reality that we can feel, faint as a whisper, across the cosmos. Let your mind drift through the spectrum of black hole sizes, a gentle gradient from small to cosmic. At the smallest theoretical end are primordial black holes, which might be no larger than an atom but contain the mass of a mountain. These tiny gravitational knots may have formed in the first moments after the Big Bang, when the universe was dense enough for small regions to collapse into black holes. Then come stellar mass black holes, formed when massive stars die and collapse. These range from a few times to dozens of times the mass of our Sun. Moving upward in the scale, we find intermediate mass black holes, thousands of times more massive than the Sun, still mysterious and rarely observed. And finally, at the magnificent end of the spectrum, we have supermassive black holes, the giants that live in galaxy centers, with masses from millions to tens of billions of suns. The largest known black hole, TON 618, weighs in at 66 billion solar masses. Its event horizon is so large that it would stretch from the Sun far beyond Neptune's orbit. This diversity is beautiful. The universe creates black holes across a vast range of scales, each playing its own role in the cosmic story. Picture this dramatic yet graceful transformation: a massive star, one that has burned brightly for millions of years, suddenly runs out of fuel for its nuclear furnace. Without the outward pressure of fusion to support it against its own gravity, the star's core collapses. And this collapse is breathtakingly fast. In less than a second, the core implodes from something the size of Earth to a point of infinite density. The outer layers, no longer supported, crash inward and then rebound in a spectacular supernova explosion that briefly outshines entire galaxies. But at the center, in the quiet eye of this cosmic storm, a black hole is born. In a fraction of a heartbeat, a structure that took millions of years to build surrenders to gravity and becomes something entirely new. It's like watching a flower bloom in reverse, a star collapsing into profound darkness in the time it takes you to snap your fingers. The universe, for all its apparent slowness, can create wonders in the blink of an eye. Imagine a black hole not as a static object but as a whirling dervish of space-time. Many black holes spin, and they can rotate incredibly fast. Some approach the speed of light at their event horizons. This rotation drags space-time itself along, creating a region called the ergosphere where nothing can remain still. Even light is pulled along in the direction of the black hole's spin. This spinning creates a kind of cosmic vortex, a whirlpool in the fabric of reality itself. The faster a black hole spins, the more energy is stored in its rotation, energy that, in principle, could be extracted by advanced civilizations. There's something almost joyful in imagining these massive objects spinning in the darkness, like celestial dancers performing pirouettes that have lasted for millions or billions of years. They spin not with effort but with inevitability, conservation of angular momentum from the star that formed them, a cosmic memory of rotation preserved forever in the structure of curved space. Let's gently clarify something beautiful. The event horizon of a black hole isn't a solid barrier or a physical surface you could touch. It's more like an invisible boundary in space, a mathematical line that marks the point beyond which escape becomes impossible. If you were falling toward a black hole and crossed the event horizon, you wouldn't bump into anything or feel a sudden change. From your perspective, space would look relatively normal, though increasingly distorted. The event horizon is simply the distance from the black hole where the escape velocity equals the speed of light. Since nothing can travel faster than light, anything that crosses this boundary must continue inward. It's a one-way membrane woven from pure geometry, a threshold written in the language of space-time curvature. Think of it not as a wall but as a commitment, a point where the future becomes fixed, where all paths lead inexorably inward. There's something almost philosophical about it, a place where turning back becomes impossible, where the only direction is forward into mystery. Here's a beautiful and disorienting thought. If you approached a black hole, the view would become increasingly surreal. The black hole's gravity bends light from distant stars and galaxies, creating a gravitational lens that warps your view of the cosmos. You'd see multiple images of the same star, stretched and curved around the black hole's silhouette. Directly ahead would be the black hole itself, a perfect dark circle, but surrounding it would be a ring of light from stars behind it, their light bent around the black hole to reach your eyes. If you got close enough, you might even see the back of your own head, your reflected light having traveled around the black hole to return to you. The entire universe would appear compressed into a bright ring surrounding the darkness, a cosmic kaleidoscope created by curved space-time. It would be like looking into a funhouse mirror designed by the laws of physics themselves, a reminder that reality near a black hole becomes fluid, flexible, and strange. There's a process with a whimsical name that describes something both fascinating and extreme: spaghettification. If you fell feet first toward a black hole, the gravity pulling on your feet would be stronger than the gravity pulling on your head, because your feet would be closer to the black hole's center. This difference in gravitational force, called a tidal force, would stretch you vertically while compressing you horizontally. The effect becomes more extreme the closer you get, eventually pulling you into a long, thin strand like a piece of spaghetti. For a stellar-mass black hole, this would happen far from the event horizon, tearing you apart long before you reach the point of no return. But remarkably, for a supermassive black hole, the tidal forces near the event horizon are much gentler. You could potentially cross the event horizon intact, experiencing spaghettification only much deeper inside. There's an odd poetry to this. The larger the black hole, the gentler your entry into its realm. It's counterintuitive but beautiful, a reminder that in the universe's mathematics, bigger can sometimes mean softer. Now picture this magnificent scene. Some black holes, rather than simply consuming everything around them, become cosmic fountains. When matter swirls around a black hole in an accretion disk, magnetic fields in the black hole's rotation can channel some of that material into narrow jets that shoot outward from the black hole's poles at nearly the speed of light. These jets can extend for thousands or even hundreds of thousands of light years, stretching across galactic distances, glowing brilliantly in radio and X-ray light. They're among the largest structures associated with any single object in the universe. How remarkable that a black hole, often imagined as purely consuming, can also create, launching fountains of energy and matter that can trigger star formation in distant regions, shaping galaxies far from the black hole itself. These jets remind us that nature loves balance. What falls and must, in some form, flow back out. The universe wastes nothing, transforms everything, and even in black holes finds ways to create beauty on the grandest scales. Let's drift into the realm of gentle speculation. In the mathematics of general relativity, black holes have theoretical opposites called white holes. While nothing can escape a black hole, nothing can enter a white hole. They would only emit matter and energy, never absorbing it. They're like black holes running backward in time. No white hole has ever been observed, and most physicists suspect they don't actually exist in our universe. But they're mathematically allowed by Einstein's equations, existing in the theoretical landscape like ghosts or echoes. Some creative thinkers have even suggested that the Big Bang itself might have been a white hole, the ultimate fountainhead from which our entire universe emerged. It's a beautiful symmetry to contemplate. If black holes are the universe's ultimate inward spirals, white holes would be its ultimate outward explosions. Even if they don't exist, the fact that the math allows them reminds us that the universe's possibilities are richer and stranger than we sometimes imagine. Reality, it seems, could have included these fountains of emergence, these anti-black holes. Perhaps somewhere, in some other universe, they do exist, creating where black holes consume. Here's something to ponder as you relax. Near a black hole, time dilation becomes so extreme that it creates a kind of temporal archive. Imagine two events happening in the universe, one near a black hole and one far away in normal space. Due to time running slower near the black hole, what takes a year far away might take only a day near the black hole. This means the black hole's neighborhood becomes a repository of slowed time, where the universe's fast-paced evolution appears to slow to a crawl. An observer near the black hole could, in theory, watch the distant universe evolve at fast-forward speeds, seeing stars born and die in what seems like moments. Meanwhile, someone far away would see the observer near the black hole moving in slow motion, as if preserved in amber. This creates an asymmetry in experience. Two parts of the universe that are fundamentally connected yet experiencing time at different rates. Black holes don't just bend space. They create wrinkles in time itself, pockets where the universe ages differently, where past and future become more flexible than we ever imagined. Despite their name and reputation, black holes aren't entirely dark. Stephen Hawking's insight revealed that quantum effects near the event horizon cause black holes to emit faint thermal radiation. This Hawking radiation arises from the strange quantum phenomenon where particle-antiparticle pairs spontaneously appear and disappear in empty space. Near a black hole's event horizon, one particle of the pair can fall in while the other escapes, making it appear as if the black hole is emitting particles. This means black holes glow very faintly, with a temperature inversely proportional to their mass. Smaller black holes glow hotter and brighter, while supermassive black holes emit only the faintest whisper of heat. It's a beautiful quantum detail. Even the universe's darkest objects participate in the dance of light and energy. Nothing in nature is truly isolated or purely anything. Even black holes, the ultimate expressions of darkness, cannot help but shine, albeit so dimly that we've never detected this light. It's still out there though, a cosmic reminder that everything radiates, everything connects, everything glows. Let your mind settle on this comforting truth: information is sacred in the universe. When something falls into a black hole, the details of what it was, its quantum information, aren't destroyed but rather encoded on the event horizon itself. This is part of what's called the information paradox, one of physics' deepest puzzles. According to quantum mechanics, information can never be truly lost, yet a black hole seems to destroy it. The resolution appears to be that the information is stored on the black hole's surface, rather than inside, and eventually re-emitted through Hawking radiation in scrambled form. So the black hole becomes like a cosmic hard drive, its event horizon covered in microscopic details about everything that ever fell in. Your story, if you fell into a black hole, would be preserved forever in its structure, encoded in subtle ripples on its surface, waiting to be released back into the universe over timescales longer than universes usually last. Nothing is forgotten. Everything leaves its mark. Picture two black holes, each perhaps tens of times more massive than the Sun, locked in orbital embrace. They spiral around each other, drawing gradually closer over millions or billions of years. As they orbit, they create gravitational waves that ripple outward through space-time, carrying away energy and causing the orbit to decay. The dance speeds up, the two black holes whirling faster and faster, approaching each other in an inward spiral that accelerates over time. In their final moments, they complete thousands of orbits per second, a cosmic waltz of unimaginable speed and power, before finally merging into a single, larger black hole in a fraction of a second. During that merger, they release more energy in gravitational waves than all the stars in the visible universe emit as light combined. It's a quiet catastrophe. No light, no sound that can travel through space, just pure gravitational energy rippling through the fabric of reality. These dances are happening throughout the universe right now, black holes embracing and becoming one, their gravitational songs propagating through the cosmos. Here's a surprisingly reassuring fact. If our sun somehow magically became a black hole, it can't, actually. It's not massive enough. Earth's orbit wouldn't change at all. The gravitational pull depends only on the sun's mass and our distance from it, not on whether it's a shining star or a dark black hole. As long as the mass stayed the same and Earth stayed at its current distance, we'd continue orbiting exactly as we do now. Of course, we'd freeze in the darkness without the sun's heat and light, but we wouldn't be sucked in. This reveals something essential about gravity. It's not about what an object looks like but about how much mass it has and where that mass is located. A black hole's gravitational pull at a distance is no stronger than the same mass in any other form. The sucking reputation of black holes is misleading. They only trap things that come very close to their event horizons. From far away, they're just massive objects with strong but ordinary gravity. It's a gentle reminder that black holes, despite their fearsome reputation, follow the same rules as everything else. They're part of nature's order, not exceptions to it. In the first fraction of a second after the Big Bang, when the universe was unimaginably dense and hot, conditions may have been right for tiny black holes to form. These primordial black holes wouldn't have come from stars. Stars didn't exist yet, but from random fluctuations in density, tiny regions slightly denser than their surroundings that collapsed under their own gravity. These black holes could range from less than the mass of a small asteroid to thousands of solar masses. Some scientists speculate that primordial black holes might make up some or all of the mysterious dark matter that we know exists but cannot see. These ancient black holes would be fossils from the universe's first moments, sealed capsules of the early cosmos preserved in gravity's embrace. They'd be wandering through galaxies now, invisible and undetected, cosmic seeds planted in the Big Bang's first breath. It's a beautiful thought, that some black holes might be older than atoms, older than light itself, witnesses to the universe's birth who have traveled 13.8 billion years to float, silent and dark, through the modern cosmos. This is called the no-hair theorem, and it's surprisingly elegant. No matter how complex the object that falls into a black hole was, whether it was a star, a planet, or a spaceship full of information, the resulting black hole can be described by just three numbers: its mass, its spin, angular momentum, and its electric charge. All other details are lost or encoded in ways we can't directly observe. This means all black holes with the same mass, spin, and charge are completely identical, indistinguishable from one another. It's as if the black hole sheds all the complicated details of its history, emerging as a pure, simple object defined only by these three fundamental properties. There's something almost zen about this. Beneath all complexity lies simplicity. Beneath all the universe's infinite variety lies a small set of fundamental quantities. Black holes are the universe stripped to its essence, reality reduced to its most basic parameters. In their featurelessness, they achieve a kind of perfection. They are what they are, nothing more, nothing less. One of astronomy's gentler mysteries is this: supermassive black holes exist in galaxies very far away, and therefore very early in cosmic history, but it's unclear how they grew so large so quickly. These black holes, with millions or billions of solar masses, appear in the universe when it was less than 1 billion years old. That's not much time for a black hole to grow from stellar mass to supermassive by slowly accumulating matter. One theory suggests these giants never went through a stellar phase at all. Instead, they formed directly from the collapse of enormous clouds of primordial gas, bypassing the star stage entirely. These direct collapse black holes might have started with tens of thousands, or even millions of solar masses right from the beginning. It's like the universe took a shortcut, creating giants without the slow process of accretion and growth. These black holes would have been anchors for the first galaxies, cosmic seeds around which stars gathered. The universe, it seems, sometimes works at scales we didn't expect, capable of creating the massive without first practicing with the small. Let's drift into quantum strangeness for a moment. In the vacuum of space, particle-antiparticle pairs constantly pop into existence and annihilate almost instantly. They're called virtual particles, and they exist for such short times that they don't violate conservation laws. Near a black hole's event horizon, though, something magical can happen. One particle of the pair can fall into the black hole while its partner escapes. The escaped particle becomes real, no longer virtual, and flies away as Hawking radiation. Meanwhile, the particle that fell in has negative energy from the black hole's perspective, causing the black hole to lose mass. So virtual particles, these quantum ghosts that normally disappear as soon as they appear, can be promoted to reality by a black hole's boundary. The event horizon becomes a kind of creation surface, where quantum possibility crystallizes into actual particles that join the universe. It's a process of making something from almost nothing, a quantum loophole that lets black holes shine and slowly evaporate. Even in the quantum vacuum's endless appearing and disappearing, black holes find ways to create lasting change. Here's something reassuring: black holes aren't cosmic vacuum cleaners that suck up everything nearby. You can orbit a black hole perfectly safely if you stay outside its event horizon, just as Earth orbits the Sun. In fact, many black holes have companion stars orbiting them in binary systems, the star's gravity and the black hole's gravity keeping them in stable orbits for millions or billions of years. The key is maintaining enough sideways velocity, Just as orbital velocity keeps the International Space Station from crashing to Earth, the same principle applies to orbiting a black hole. You'd need to be moving fast, very fast, but it's possible in principle. Closer orbits would require higher speeds, and there's an innermost stable circular orbit beyond which no stable orbit exists. But above that distance, you could circle a black hole indefinitely, watching the universe from your unique vantage point where time runs slower and light bends strangely. It's not recommended as a travel destination, but it's nice to know that black holes can be neighbors, not necessarily destroyers. As you drift toward rest, consider this mind-bending possibility. Some cosmologists have suggested that our universe might exist inside a black hole. The idea emerges from the mathematical similarity between the expanding universe described by Big Bang cosmology and the interior of certain types of black holes. From inside a black hole, an observer wouldn't see the singularity as a point in space but as a moment in time, an inevitable future that everything is falling toward. Similarly, in our universe, the Big Bang is not a point in space but a moment in time that everything originated from. The parallels are intriguing. Could every black hole contain an entire universe? Could our universe be a black hole in some larger parent universe? The math doesn't prove it, but it allows it, and the idea has a beautiful recursiveness to it. Universes within universes, reality nested like matryoshka dolls. It's unprovable with our current understanding, but that makes it no less fascinating as a thought. Perhaps creation and destruction are more intimately connected than we realize. Perhaps every ending births a beginning we cannot see. Through gravitational lensing, black holes can act like cosmic magnifying glasses. When a black hole passes between us and a distant star or galaxy, the black hole's gravity bends the light from that background object around itself. This can create multiple images of the background object, stretched into arcs or rings, and can actually make the background object appear brighter than it would without the lens. This brightening is called gravitational amplification, and it's helped astronomers study distant galaxies that would otherwise be too faint to see in detail. The black hole, despite being dark itself, illuminates the universe beyond it, focusing and intensifying light that passes nearby. It's a beautiful irony, one of the universe's darkest objects helping us see some of its most distant lights more clearly. Einstein predicted this effect decades before it was observed, another triumph of general relativity, another example of how black holes, for all their strangeness, follow mathematical laws we can understand and use to explore the cosmos. At the heart of our own galaxy lives a supermassive black hole called Sagittarius A, SGRA, with a mass of about 4 million suns. You might expect such a massive object to be violently consuming matter, blazing with energy. But SGRA is remarkably quiet, it's barely active, accreting matter at a very slow rate. Most of the time it's dim, occasionally flaring slightly when a clump of gas or an unlucky star passes too close. This quietness is fortunate for life in our galaxy. An actively feeding supermassive black hole can blast its surroundings with deadly radiation. Our black hole is in retirement, having already grown to its current size, now just existing peacefully while stars orbit around it. The closest stars circle it at speeds of thousands of kilometers per second, completing orbits in mere years despite being light days away from the black hole. Astronomers have tracked these stars' orbits for decades, watching them loop around the invisible massive presence at the galaxy's center. It's like a cosmic lighthouse that's almost turned off, its presence known only by the motion of stars dancing around darkness. Let's return to the beautiful strangeness of time near black holes. Imagine you had a spacecraft hovering just outside a black hole's event horizon, an extremely powerful spacecraft to maintain position against the immense gravity. If you spent what felt like one day there, when you returned to Earth, years, decades, or even centuries might have passed, depending on how close you were. This isn't just a mathematical curiosity, it's a real effect of general relativity, confirmed through precision measurements with atomic clocks. Time itself is not universal but local, flowing at different rates depending on gravity and velocity. Near a black hole, you'd experience time normally. Each second would feel like a second, but you'd be moving through time slower relative to the universe far from the black hole. It's like being in a protected bubble where the universe's frantic pace slows to stillness. Science fiction often uses this for time travel, but it's real physics, a gentle reminder that time itself is flexible, that simultaneity is an illusion, and that the universe's clock ticks differently in different places. Imagine the universe in the deep future, trillions upon trillions of years from now. All the stars have exhausted their fuel and gone dark. Galaxies have dispersed. The cosmos has grown cold and empty. In this far epoch, black holes will be among the last structures remaining, slowly evaporating through Hawking radiation. The smaller ones will go first, having higher temperatures and radiating faster. The stellar mass black holes will take about 10 to the power of 67 years. The supermassive ones, those galactic giants, will persist for 10 to the power of 100 years or more, a number so large it defies comprehension. But eventually, even these will fade, their mass converted entirely to radiation, leaving nothing behind but a faint whisper of photons spreading through the darkness. In that ultimate future, the black holes won't disappear with drama but with a quiet sigh, a final gentle emission of light before they cease to be. They will have been the universe's last monuments, the final holdouts against entropy, before they too surrender and become pure energy. It's a melancholy beauty, that even the cosmos's most enduring structures are temporary, that everything eventually returns to light. The black hole information paradox has puzzled physicists for decades, and its resolution is elegant and subtle. When matter falls into a black hole, its quantum information, the detailed description of every particle's state, doesn't vanish. Instead, it becomes encoded in the Hawking radiation that the black hole emits as it evaporates. The information comes back out, but in a scrambled, encrypted form, like a book whose pages have been shredded and mixed randomly. In principle, someone with enough computing power could reconstruct the original information from the pattern of emitted radiation, though in practice it would be impossibly difficult. This means black holes are like the universe's shredders. They scramble information so thoroughly that it appears destroyed, but the information is technically still there, hidden in correlations between the particles of Hawking radiation. The universe, it seems, keeps perfect records, even if those records are written in code so complex we can barely imagine deciphering it. Nothing is truly forgotten. Everything is merely transformed into a new language. Spinning black holes have a fascinating region called the ergosphere, between the event horizon and a slightly larger boundary. Within this region, space-time itself is dragged along by the black hole's rotation. Everything must move in the direction of the spin, even light. But here's the remarkable part. It's possible to enter the ergosphere and leave it with more energy than you came in with, extracting energy from the black hole's rotation itself. This is called the Penrose process, named after physicist Roger Penrose who discovered it. You'd send something into the ergosphere, have it split into two pieces, arrange for one piece to fall into the black hole with negative energy, from the black hole's perspective, and the other piece escapes with extra energy, energy stolen from the black hole's spin. This isn't science fiction, it's allowed by the mathematics of general relativity. An advanced civilization could theoretically harness this to power itself using a spinning black hole as an engine. The black hole would slowly spin down over time, its rotational energy converted to useful work. It's one of the universe's most elegant power generation schemes, waiting in the equations for someone clever enough to use it. At the very center of a black hole lies the singularity, the point where, according to general relativity, density becomes infinite, and the curvature of spacetime becomes infinite. But here's the gentle truth: physicists don't really believe the singularity exists as a physical thing. Instead, it's where our current theories stop working, where the equations produce infinities that signal we're missing something. Most likely, quantum effects become important at extremely small scales, and a quantum theory of gravity would replace the singularity with something else. Perhaps a region of extremely dense but finite matter, or perhaps something we can't yet imagine. The singularity is less a real place and more a signpost saying, "Our map ends here." It's humbling and exciting at once. Humbling because it shows the limits of our current understanding, exciting because it points to deep mysteries still waiting to be solved. Inside a black hole may lie secrets about the nature of space, time, matter, and reality itself, secrets that will only reveal themselves when we finally unite quantum mechanics and gravity into a single theory. When Einstein published his theory of general relativity in 1915, it predicted the existence of black holes, though Einstein himself didn't believe they were real. The equation showed that if enough mass concentrated in a small enough region, spacetime would curve so severely that not even light could escape. For decades, these solutions were considered mathematical curiosities. But as astronomers discovered increasingly massive collapsed objects, first neutron stars, then evidence of something even more compact, black holes transition from theoretical possibility to observed reality. The detection of gravitational waves from merging black holes in 2015 was perhaps the strongest confirmation yet, matching Einstein's predictions with remarkable precision. Black holes have become one of general relativity's greatest triumphs, exotic predictions that turned out to be real features of our universe. They're living laboratories for testing gravity in its most extreme forms. And so far, Einstein's century-old theory passes every test. It's beautiful how the universe validates our mathematics, how equations written in quiet offices describe the behavior of massive objects billions of light years away. Some theories predict that if extra dimensions exist beyond the three of space and one of time we're familiar with, it might be possible to create tiny black holes and high-energy particle collisions, like those at the Large Hadron Collider. These micro-black holes would be incredibly small, far smaller than an atom, and would evaporate almost instantly through Hawking radiation, lasting only 10 to the power of negative 27 seconds before disappearing in a puff of particles. They'd pose no danger. They'd be gone before they could absorb anything. Despite sensationalist fears when the LHC was being built, physicists are confident these tiny black holes, if they form at all, are harmless. In fact, if they were detected, it would be an exciting discovery, providing evidence for extra dimensions and allowing us to study Hawking radiation directly for the first time. The universe might be creating these micro-black holes naturally all the time in cosmic ray collisions high in Earth's atmosphere. It's another reminder that black holes come in all scales, that the same physics that governs galactic giants might also apply to quantum-scale specks that live and die in less than a trillionth of a second. One of the gentlest ways to picture how black holes curve spacetime is to imagine space as a stretched rubber sheet. Place a bowling ball on the sheet, and it creates a depression, a well. Objects moving across the sheet will curve toward the depression, and if they get too close, they might spiral inward. A black hole's gravity well is similar but far more extreme. The depression becomes infinitely deep, a bottomless pit in the fabric of space itself. The event horizon is where the walls of the well become vertical, where the slope becomes so steep that no sideways motion can escape. This visualization isn't perfect. It uses a two-dimensional sheet to represent three-dimensional space, but it captures something essential about how mass curves the geometry around it. Objects don't fall into black holes because they're being pulled by a force. They fall because they are following the straightest possible paths through curved spacetime, and those paths lead inward. The black hole isn't reaching out to grab things, it's simply existing, and its existence changes the very shape of space, creating valleys in the landscape of reality. Imagine an advanced civilization that has learned to harness a black hole's energy. They could drop matter into the black hole and capture the tremendous energy released as that matter accelerates and heats up in the accretion disk, as much as 10% to 40% of the matter's mass energy, far more efficient than nuclear fusion. Or they could extract rotational energy through the Penrose process. Or they could build a massive sphere around the black hole to capture all the radiation from the accretion disk, a black hole-powered Dyson sphere. Such a civilization could maintain its energy needs for billions or even trillions of years, far longer than any star-based energy source would last. The black hole would be like an eternal engine, a cosmic power plant that grows larger and more powerful as it's fed. In science fiction, these scenarios are often explored, but they're based on real physics. A black hole could be the ultimate renewable energy source for a sufficiently advanced society. It's a hopeful thought that the universe provides not just stars to warm us but also black holes that, properly understood, could power civilizations through the deep epochs when stars have all burned out. The very first stars in the universe, called population 3 stars, formed from pure hydrogen and helium. No heavier elements existed yet because they hadn't been created by earlier stellar generations. These primordial stars may have been true monsters, ranging from 100 to 1,000 times the mass of the Sun, burning hot and bright but living only a few million years. When they died, they would have collapsed directly into black holes, likely without the dramatic supernova explosion typical of smaller massive stars. These black holes would have been some of the first black holes formed after the Big Bang. Aside from primordial black holes, seeds planted in the universe's youth. Some of them may have eventually grown into the supermassive black holes we see today at galaxy centers. They're fossils in a sense, remnants of a vanished population of stars we've never directly observed, preserved as dark gravitational memories. These ancient black holes have witnessed almost the entire history of the cosmos, from the universe's first light through 13 billion years of cosmic evolution. Here's a beautiful rule of the universe. The second law of black hole thermodynamics states that the total surface area of all event horizons in the universe can never decrease. When black holes merge, the resulting black hole always has a larger surface area than the sum of the two original black holes. When matter falls in, the surface area increases. Even when black holes evaporate through Hawking radiation, the radiation carries entropy that compensates for the decrease in the black hole's area. This parallels the second law of thermodynamics, which states that entropy, disorder, in a closed system never decreases. In fact, the analogy is so deep that physicists believe black hole entropy is proportional to the event horizon's surface area. Measured in Planck units, there's approximately 1 bit of information stored for each square Planck length of the event horizon. So black holes are not just objects but rather cosmic repositories of entropy. Their surfaces encoded with the maximum amount of disorder and information they can hold. The universe keeps careful accounts, and black holes are the ledgers where the cosmos records its history. If you watch someone fall toward a black hole's event horizon, you'd witness something both beautiful and strange. As they approach the boundary, they'd appear to slow down. The light from them would redshift, becoming dimmer and redder. They'd get closer and closer to the horizon, but from your perspective watching safely from far away, they'd never quite reach it. Time dilation would stretch their descent infinitely. Mathematically, it would take infinite time for them to cross the horizon as measured by your distant clock. They'd appear frozen just above the event horizon, their image fading and reddening but never disappearing completely. From their perspective, though, They'd cross the horizon in finite time, experiencing nothing special at the boundary itself. This asymmetry reveals something profound about time and perspective. There's no universal now in the universe, no single timeline everyone shares. Different observers experience time differently, and near black holes, these differences become extreme. The falling person and the distant observer are living through the same event but experiencing it in fundamentally incompatible ways, each perspective equally valid, each reality equally real. Thanks to Hawking radiation, black holes have a temperature. They emit thermal radiation like any hot object. But there's a wonderful inversion. Smaller black holes are hotter, while larger ones are cooler. A black hole with the mass of the Sun would have a temperature of about 60 nanokelvins, incredibly cold, far colder than the cosmic microwave background radiation that fills the universe. But a black hole with the mass of a mountain would have a temperature of thousands of degrees. A micro black hole the mass of a building might glow white-hot. The temperature is inversely proportional to mass. Cut the mass in half, and the temperature doubles. This means as a black hole evaporates and loses mass, it gets hotter, which makes it evaporate faster, which makes it hotter still, a runaway process that ends in a final flash of radiation as the last of the black hole disappears. The universe's smallest black holes, if they exist, would be the hottest objects imaginable, glowing brilliantly with Hawking radiation before vanishing in bursts of high-energy particles. Even in thermodynamics, black holes follow their own inverted logic. Here's something counterintuitively comforting. If you fell into a supermassive black hole, not a stellar mass one, but one of the galactic giants with millions or billions of solar masses, you could cross the event horizon and survive for a while, possibly minutes, or even hours. The tidal forces at the event horizon of such a massive black hole are relatively gentle because the horizon is so far from the central singularity. You wouldn't feel anything special as you cross the point of no return. Looking around, you'd see the universe behind you blue shifted and compressed into a bright ring, while ahead would be darkness punctuated by the glowing accretion disks light bent and distorted. Only as you fell deeper, approaching the singularity, would tidal forces grow strong enough to spaghettify you. For a while, you'd be in a strange realm where escape was impossible but destruction hadn't yet occurred, existing temporarily in a place between, falling toward inevitable doom but not yet experiencing it. It's both terrifying and oddly peaceful, a final journey through curved spacetime before physics as we know it ceases to apply. When two black holes merge, the amount of energy they release in gravitational waves is staggering. In the first detection by LIGO, two black holes merged about 1.3 billion light-years away. In the final fraction of a second of their merger, they radiated about 3 times the mass of the Sun purely in gravitational wave energy, converted directly from matter to gravitational radiation via E=mc². For that brief moment, the merger outshone, in gravitational waves, all the stars in the observable universe combined. No electromagnetic radiation, no light, no radio waves, just space-time itself rippling with energy. These are the most energetic events in the universe since the Big Bang itself. Yet they're invisible to our eyes, silent to our ears, detectable only by the most sensitive instruments ever built. It's humbling to know the universe hosts such titanic events regularly, collisions of dark giants releasing more energy than billions of exploding stars, all happening in silence, hidden from ordinary observation. The universe's greatest concerts are played in frequencies we cannot naturally hear, on instruments made of gravity itself. In the mathematics of general relativity, certain solutions suggest that black holes might be connected to other regions of spacetime through tunnels called wormholes, or Einstein-Rosen bridges. A wormhole would connect the interior of a black hole to a white hole, its theoretical opposite, in another location, perhaps in another part of our universe or even in another universe entirely. You could theoretically enter a black hole and emerge somewhere else. However, the math also suggests these wormholes are unstable. They'd collapse faster than anything could traverse them unless held open by exotic matter with negative energy density, which may not exist. So while wormholes are mathematically possible, they're probably not physically real, at least not in a form useful for travel. Still, they populate the theoretical landscape, reminders that general relativity allows for extraordinary space-time structures. The equations hint at connections, shortcuts, tunnels through reality. Even if we can never use them, their possibility enriches our understanding of what space-time can do, how flexible and strange its geometry might be. When galaxies collide and merge, their central supermassive black holes eventually meet. Before they merge, they orbit each other, and as they spiral inward, they can reach enormous velocities, up to a significant fraction of the speed of light. Picture two objects, each millions of times more massive than the Sun, whirling around each other at thousands or tens of thousands of kilometers per second. The energy involved is almost incomprehensible. These, final parsec, orbits create powerful gravitational wave emission that eventually brings the black holes together. During galaxy collisions, which take hundreds of millions of years to complete, the universe stages its grandest dances, entire galactic cores restructuring themselves while their central black holes perform a deadly orbital ballet. When they finally merge, the gravitational waves they produce can travel across billions of light years of space. Some of those waves are passing through Earth right now, stretching and squeezing space by imperceptible amounts, whispers from collisions that happened eons ago in distant corners of the cosmos. The nearest black hole to Earth that we've identified is about 1,000 light-years away, a stellar mass black hole that's part of a binary system with an ordinary star. There may be closer ones we haven't detected yet, possibly even a few hundred light-years away, but they're hard to find if they're not actively accreting matter or influencing nearby stars obviously. This distance is reassuring. Even the closest black hole is far beyond the reach of any conceivable journey with current or near-future technology. In one way, it's frustrating. We'd love to study black holes up close. But in another way, it's comforting. We live in a peaceful region of the galaxy, far from these exotic objects, able to observe them safely from a distance. Our sun will never become a black hole. It lacks the mass. The nearest black holes will never come close enough to affect Earth. We're cosmic bystanders, observing from the stands rather than playing on the field, which is exactly where we want to be when the game involves objects that can trap light itself. We've reached the halfway point in our journey, and it's worth pausing to reflect. Black holes force us to confront the limits of our intuition. They show us that time is not universal, that space can be curved, that information and entropy are deeply connected, that singularities might lurk at the hearts of these objects, and that the universe operates on principles far removed from everyday experience. They challenge our notions of what exists means. Can something be real if no information can ever escape from it? They blur the boundaries between thermodynamics, quantum mechanics, and gravity. Every new discovery about black holes reveals not just facts about these objects but deeper truths about reality itself. They're not just astronomical curiosities but rather windows into the fundamental nature of the cosmos. As you drift deeper into rest, let this sink in. The universe is far stranger, far more interesting, and far more beautiful than human imagination alone could have invented. Black holes are proof that reality exceeds fiction, that the cosmos is weirder and more wonderful than our dreams. Not all black holes are nestled safely in galaxy centers or binary systems. Some are rogues, wandering through the vast emptiness between galaxies. These can form when galaxies merge and their central supermassive black holes receive a gravitational kick from the merger, flinging one of them out of the galaxy entirely at speeds of thousands of kilometers per second. These rogue black holes travel alone through intergalactic space, dark and nearly undetectable unless they happen to pass through a cloud of gas, which would briefly light up as it heats from accretion. There may be millions of these wanderers in the universe, solitary giants crossing the cosmic voids, no longer anchoring galaxies but drifting freely through the expanding space between them. It's a lonely existence, moving through near emptiness for billions of years, encountering nothing, just traveling on momentum granted by a violent past. Yet there's something poetic about them too, free from gravitational bonds, explorers of the universe's largest empty spaces. In 1974, Stephen Hawking published a paper that revolutionized our understanding of black holes. Until then, black holes were thought to be perfect traps. Absolutely nothing could escape once it crossed the event horizon. Hawking showed, through an elegant combination of quantum mechanics and general relativity, that black holes must emit radiation and therefore slowly evaporate. This was shocking because it meant black holes have temperature and entropy, connecting them to thermodynamics in unexpected ways. It also meant black holes aren't permanent. Given enough time, they'll disappear completely. Hawking's insight opened entire new fields of research and deepened the mystery surrounding black holes, particularly the information paradox. It's beautiful how one person's deep thinking can change our entire perspective on cosmic objects. Hawking radiation itself has never been directly detected. It's far too faint for any real black hole we can observe, but it's become a cornerstone of theoretical physics. The universe rewards careful thought with revelations, and Hawking's revelation was that even darkness cannot help but shine. Some of the universe's most energetic phenomena are the jets launched by actively feeding black holes. These jets, shooting from the poles of spinning black holes at nearly light speed, can extend for millions of light years, punching through their host galaxies and far into intergalactic space. The jets carry tremendous energy, heating the gas around them, creating vast bubbles in the intergalactic medium, and influencing star formation across entire galaxies. In some cases, these jets provide negative feedback. They heat gas so much that it can't cool down and collapse to form new stars, effectively regulating their galaxy's growth. The black hole, rather than just consuming its galaxy, helps shape and control it, maintaining a balance between star formation and gas consumption. These jets are visible in radio wavelengths, creating enormous cosmic sculptures, loops, bubbles, and filaments of energized gas spanning galactic scales. A single black hole, sitting in a galaxy's center, can exert influence across regions larger than the galaxy itself, sculpting the cosmos through jets of matter and energy. There's a beautiful cosmic configuration called Einstein's cross, where light from a distant quasar passes close to a foreground galaxy with a massive black hole at its center. The gravity bends the quasar's light around the galaxy, creating 4 separate images of the same quasar arranged in a cross pattern around the lensing galaxy. From Earth, we see one quasar appearing in 4 different places, all equally bright, surrounding the gravitational lens. It's like looking through a cosmic kaleidoscope created by warped spacetime. This phenomenon allows astronomers to study both the distant quasar and the lensing black hole simultaneously. The light taking different paths around the lens arrives at different times too, so if the quasar flickers, the 4 images flicker at slightly different times. We see the same event happening multiple times, echoes separated by days or weeks. Einstein's cross is one of nature's most photogenic demonstrations of general relativity, a stunning visual proof that mass bends light, that space-time has texture and curvature. The universe creates art with its own physics, arranging light and gravity into patterns that delight the eye and mind alike. In the distant universe, visible when looking billions of light years away, and therefore billions of years into the past, we see incredibly bright objects called quasars, quasi-stellar radio sources. These are supermassive black holes actively consuming enormous amounts of matter, sometimes dozens of solar masses per year. The material heats to millions of degrees as it spirals inward, creating accretion disks so bright they outshine their entire host galaxies. A single quasar can be 1,000 times more luminous than the Milky Way, all that energy coming from a region smaller than our solar system. Quasars were more common in the early universe when galaxies were still forming and had more gas to feed their central black holes. Today, most supermassive black holes, including our own galaxies, are relatively quiet. They've either consumed most of their nearby gas or it's been blown away. Quasars are black holes at their most dramatic, cosmic beacons showing what happens when these gravitational giants feast rather than fast. They're loud where modern black holes are quiet, brilliant where they're dark, evidence of a more active, violent cosmic youth. If you wanted to travel to the future, say, to see what Earth is like in 10,000 years, you could theoretically do it using a black hole. Take a spacecraft near the event horizon of a supermassive black hole, carefully maintaining your position for what feels like a few years. Due to time dilation, those years for you could equal 10,000 years for someone back on Earth. When you returned, you'd step into Earth's far future, having aged only a few years while millennia passed in the outside universe. This isn't science fiction, it's real physics, though practically impossible with current technology. The energy required to hover near a black hole's event horizon, fighting against gravity that wants to pull you in, is almost unimaginable. But the principle is sound. Time dilation is a proven effect, and black holes provide the most extreme gravitational environments to exploit it. In this way, black holes are time machines of a sort, gateways to the future for those brave or desperate enough to approach them. You can't go backward in time, but forward? The universe permits that, written in Einstein's equations, waiting for anyone who dares. When a black hole spins, it doesn't spin through space, it drags space itself along with it. This effect, called frame dragging or the lens stirring effect, means that near a spinning black hole, space-time itself rotates. If you tried to remain stationary, you'd find it impossible. You'd be swept along in the direction of the spin like a stick caught in a whirlpool. Closer to the black hole, the dragging becomes stronger. Within the ergosphere, even light is forced to move in the direction of the rotation. This creates strange effects. Gyroscopes near a spinning black hole would press us. Orbital planes would shift. Everything with mass would be caught in the rotating flow of spacetime itself. It's one of general relativity's most mind-bending predictions, confirmed through observations of jets and accretion disks around black holes. Space is not a fixed stage on which events occur, it's a dynamic participant, especially near massive rotating objects. A spinning black hole carries its cosmic neighborhood along with it, creating a swirling region where spacetime itself rotates like water circling a drain. Despite decades of work, physicists still debate what happens to information that falls into a black hole. Quantum mechanics says information cannot be destroyed. The quantum state of a system always evolves in a way that preserves information. But a black hole seems to destroy information, hiding it behind the event horizon where it can't be retrieved. When the black hole eventually evaporates through Hawking radiation, where did that information go? Hawking originally thought it was lost, violating quantum mechanics. Others argued it must be preserved somehow, perhaps encoded in the Hawking radiation. Recent ideas involving holography suggest the information is stored on the event horizon's surface. The paradox has inspired new theories about spacetime, quantum mechanics, and the connections between them. It remains unsolved, though progress is being made. What makes it beautiful is how it connects deep questions about information, entropy, thermodynamics, quantum mechanics, and gravity. Black holes, by simply existing, pose philosophical and physical puzzles that challenge our understanding of reality at its most fundamental level. They are questions as much as they are objects. Here's a more unsettling proposal from some physicists. Maybe crossing a black hole's event horizon isn't gentle after all. The firewall hypothesis suggests that to preserve quantum information and avoid paradoxes, there must be a region of extreme energy, a firewall, right at or just inside the event horizon. Anything crossing this boundary would be instantly incinerated by intense radiation, contradicting the classical picture where you'd cross smoothly without noticing. This idea is controversial and creates its own problems, particularly with the equivalence principle, a cornerstone of general relativity that says freely falling observers shouldn't experience anything special at the event horizon. The firewall debate shows how trying to reconcile quantum mechanics with gravity leads to strange, sometimes contradictory conclusions. We don't know if firewalls exist or if some other resolution to the paradoxes is correct. It's humbling. Even after a century of studying these objects, fundamental questions about what happens at their boundaries remain open, mysteries that will require new physics to resolve. The deepest challenge in modern physics is finding a theory that unifies quantum mechanics, which governs the small, with general relativity, which governs the large and massive. Black holes sit precisely at the intersection. They're massive enough to create extreme gravitational effects described by general relativity, yet their singularities are small enough that quantum effects should dominate. This makes black holes natural laboratories for testing theories of quantum gravity. String theory, loop quantum gravity, and other approaches all make predictions about what happens at black hole singularities and event horizons. Observations of Hawking radiation, if we can ever detect it, measurements of black hole entropy, and studies of information preservation all provide clues about how gravity and quantum mechanics must ultimately fit together. When physicists finally develop a successful quantum theory of gravity, black holes will likely be central to that breakthrough. They're not just curiosities but signposts pointing toward a deeper understanding of the universe. By studying black holes, we're working toward a more complete picture of reality, one where quantum effects and gravitational effects merge seamlessly into a single framework. Current models suggest that supermassive black holes and their galaxies grew together, co-evolving over billions of years. The black hole's mass is proportional to the mass of the galaxy's central bulge, hinting at a deep connection between galaxy formation and black hole growth. The black hole may have provided the gravitational seed around which gas could collect and form stars. Or perhaps large gas clouds collapsed simultaneously to form both the galaxy and its central black hole. Throughout their histories, galaxies and their black holes influenced each other. Black hole jets and winds regulated star formation, while infilling matter helped the black hole grow. This symbiotic relationship shaped the universe we see today, with almost every substantial galaxy harboring a supermassive black hole at its core. We're beginning to understand that galaxies aren't just collections of stars with black holes coincidentally in their centers. Rather, the black holes are integral to galactic evolution, partners in the cosmic dance of structure formation. Understanding this relationship helps explain why galaxies look the way they do and why the universe has evolved along the particular path we observe. In the first few 100,000 years after the Big Bang, the universe was filled with a hot plasma of matter and radiation. Sound waves, pressure waves, rippled through this plasma, creating regions of higher and lower density. When the universe cooled enough for atoms to form and matter to decouple from radiation, these density fluctuations were frozen in place. The denser regions eventually collapsed under gravity to form the first stars and galaxies. Some theories suggest that particularly dense regions might have collapsed directly into black holes without first forming stars. These primordial black holes would carry with them acoustic imprints from the Big Bang, frozen echoes of sound waves that traveled through the infant universe. By studying the distribution and properties of ancient black holes, we might someday read the acoustic signature of the universe's first moments, hearing in black hole statistics the echo of cosmic sound waves from the dawn of time. The universe may have written its early history not just in light but in gravity, encoding its first songs into the distribution of black holes across space. Black hole physics has led to one of the most startling ideas in theoretical physics, the holographic principle. It suggests that all the information contained in a volume of space can be represented by information encoded on the boundary of that space, like a 3D image encoded in a 2D hologram. This idea emerged from studying black hole entropy, which is proportional to the event horizon's surface area rather than its volume. If black holes follow this pattern, perhaps the entire universe does too. Maybe our three-dimensional reality is actually information encoded on a distant two-dimensional surface, and everything we experience, depth, solidity, existence itself, emerges from that encoding. It sounds like science fiction, but it's taken seriously by physicists working on quantum gravity. The holographic principle suggests reality is fundamentally different from how it appears, that dimensions might be less fundamental than we thought, that the universe's structure is more mathematical and information-based than physical. Black holes, by forcing us to think about information and entropy in new ways, have opened philosophical doors we never knew existed. As you continue to relax, consider this. Black holes were predicted mathematically before they were observed. Einstein's equations, worked out in quiet thought using nothing but logic and math, predicted that such objects must exist. For decades they remained theoretical curiosities. Then astronomers found evidence, X-ray sources, orbital anomalies, quasar energetics, and finally gravitational waves and photographs. Every prediction was confirmed. The universe, it turns out, actually works the way the math says it should, even when the math describes things as strange as black holes. This is deeply reassuring in a way. It means the universe is comprehensible, that human thought can grasp its workings, that patient investigation reveals truth. Black holes reward our curiosity with answers, even when those answers are stranger than the questions. They teach us that the cosmos operates on principles we can discover, that reality is mathematical at its core, and that the patient work of science eventually illuminates even the darkest corners of existence. In black holes, we see proof that the universe makes sense, even when that sense is profoundly counterintuitive. We know about stellar mass black holes, from a few to dozens of solar masses, formed from dying stars. We know about supermassive black holes, millions to billions of solar masses, sitting in galaxy centers. But between these two extremes, from about 100 to 100,000 solar masses, lies a mysterious gap. These intermediate mass black holes should exist, but we've found very few convincing candidates. They're too massive to form from single stellar collapses but too small to be the supermassive giants. Perhaps they form when stellar mass black holes merge repeatedly in dense star clusters, growing step by step. Perhaps they're the seeds that eventually grow into supermassive black holes. Or perhaps they form through some other process we haven't yet imagined. Finding these intermediate black holes is one of astronomy's current quests, a hunt for the missing link in black hole evolution. They're shy, hard to detect, hiding in environments that make them difficult to study. But occasional glimpses suggest they're out there. X-ray sources in globular clusters, gravitational wave signals from unusually massive mergers. Each discovery fills in more of the picture, connecting the dots between stellar remnants and galactic giants. The universe likely makes black holes across the full spectrum of masses. We just need to find them all. After the Big Bang, the universe went through a period called the Dark Ages, when neutral hydrogen gas filled space and absorbed most light. Then, gradually, This gas was reionized. Its electrons were stripped away again, allowing light to travel freely. For decades, astronomers thought only stars provided the energy for reionization. But recent research suggests black holes, particularly those powering quasars in the early universe, may have contributed significantly. The intense radiation from matter falling into early black holes could have ionized vast regions of space, creating bubbles of transparent, ionized gas that eventually merged to fill the universe. Black holes, rather than being passive bystanders, actively shaped the conditions that made the universe transparent to light. They helped in the Dark Ages, transforming the cosmos from opaque to clear, from dark to bright. It's remarkable how these objects, often associated with darkness, actually contributed to illuminating the universe, their violent feeding episodes in the cosmic dawn helping to clear the fog that filled space, allowing light to travel and galaxies to become visible across billions of light years. Every object has a Schwarzschild radius, the radius within which, if all its mass were compressed, it would become a black hole. For Earth, that radius is about 9 millimeters. For the Sun, it's about 3 kilometers. These objects aren't black holes because their actual matter extends far beyond these radii, but compress Earth to smaller than 9 millimeters across, and the Schwarzschild radius would become its event horizon. The radius grows linearly with mass, double the mass, double the Schwarzschild radius. This simple relationship, derived from Einstein's equations by Karl Schwarzschild in 1916 while he was serving in World War I, defines the critical boundary of every black hole. It's beautiful in its simplicity. One equation connecting mass, the speed of light, and the gravitational constant determines where spacetime curves so severely that escape becomes impossible. Schwarzschild found this solution shortly after Einstein published general relativity, working out the math in the trenches of war, showing that even in humanity's darkest moments, minds can reach toward cosmic truths. The radius bearing his name now defines one of the universe's most fundamental boundaries. Around active black holes, charged particles can be accelerated to incredible energies, approaching the speed of light. The magnetic fields threading through accretion disks and jets act like cosmic particle accelerators, far more powerful than anything we can build on Earth. These accelerated particles produce intense radiation across the electromagnetic spectrum: radio waves, X-rays, gamma rays. Some particles escape in jets, traveling across vast distances still carrying enormous energy. When these high-energy particles strike other matter or radiation, they create cascades of secondary particles, cosmic ray showers that spread through space. Black holes, in this way, are the universe's most powerful natural accelerators, creating particles with energies millions or billions of times higher than the Large Hadron Collider achieves. They're laboratories for extreme physics, testing particle behavior at energies and field strengths impossible to replicate on Earth. By studying the radiation from active black holes, we learn about physics in its most extreme forms, expanding our understanding of how matter and energy behave when pushed to their limits. Despite forming from the collapse of complex, information-rich objects, stars with intricate internal structures, planets, spacecraft, whatever falls in, a black hole itself is described by just 3 numbers: mass, spin, and electric charge. This is called the no-hair theorem, hair being a metaphor for unnecessary details. No matter how complicated the infilling matter was, the resulting black hole is simple, characterized completely by these 3 parameters. 2 black holes with identical mass, spin, and charge are completely indistinguishable, even if one formed from matter and one from antimatter, even if one formed 1,000,000 years ago and one formed yesterday. All the details, chemical composition, temperature, history, are erased or hidden behind the event horizon. This simplicity is both elegant and puzzling. Where did all that information go? Is it truly erased, or merely inaccessible? The no-hair theorem suggests black holes are nature's ultimate minimalists, shedding all unnecessary complexity to exist as pure gravitational solutions to Einstein's equations. They're what remains when you strip away everything except the most fundamental properties. The same quantum processes that create Hawking radiation near black holes are happening everywhere, all the time, even in the empty space around you. Virtual particle-antiparticle pairs spontaneously appear and annihilate constantly due to quantum uncertainty. In normal space, far from black holes, these pairs always recombine and vanish, their existence so brief they leave no lasting trace. But near a black hole's event horizon, the immense gravitational gradient can separate these pairs before they recombine, making one real while the other falls in. Even as you rest, the quantum vacuum around you is buzzing with these ephemeral pairs, electrons and positrons, quarks and antiquarks, blinking in and out of existence. We call it empty space, but quantum mechanics reveals it's actually seething with activity at scales too small and too brief for us to directly observe. Black holes simply exploit this quantum foam, turning virtual particles into real ones through the physics of their event horizons. The vacuum isn't empty, it's alive with potential, with quantum possibility constantly manifesting and vanishing in the smallest corners of reality. Before 2015, all our knowledge of the universe came from electromagnetic radiation, light in all its forms. Then LIGO detected gravitational waves, and we opened a new sense, a new way of experiencing the cosmos. Gravitational waves are ripples in spacetime itself, carrying information about their sources and the patterns of their oscillations. When black holes merge, they create these waves, and by studying the waves' frequency, amplitude, and evolution, we can determine the masses and spins of the merging black holes, their distance from us, even the orientation of their orbital plane. It's like hearing a musical note and being able to tell what instrument played it, how far away the musician was, and what materials the instrument was made of. Gravitational wave astronomy is still in its infancy, but it's already revolutionizing our understanding of black holes, revealing populations of them we didn't know existed, confirming that binary black hole mergers are common, and providing tests of general relativity in extreme conditions. We're learning to listen to the universe's gravitational music, hearing the cosmos in a way our ancestors could never have imagined. In the early universe, within a few 100 million years after the Big Bang, the first black holes formed, either from the first stars or directly from collapsing gas clouds. These black holes may have served as gravitational anchors, seeds around which gas could accumulate. Their gravity would attract nearby matter, creating dense regions that became the sites of galaxy formation. Without these early black holes, galaxies might have formed differently, perhaps more slowly or in different configurations. The black holes also provided energy feedback. As they accreted matter, they heated their surroundings, regulating how quickly stars could form. This delicate balance between black hole growth and galaxy growth shaped the universe's large-scale structure. The galaxies we see today may owe their existence, at least in part, to black holes planted in the cosmic dawn. It's a beautiful inversion of the usual narrative. We often think of galaxies hosting black holes, but perhaps black holes hosted the first galaxies, providing the gravitational framework around which stellar communities could gather and grow. Let your mind drift into speculative territory now. Some physicists have proposed that inside every black hole, beyond the event horizon and singularity, might lie an entire new universe. When matter collapses to extreme density, perhaps it doesn't form a true singularity but instead undergoes a kind of quantum bounce, expanding outward into a new spacetime, a baby universe disconnected from our own. From our perspective, it looks like a black hole. From the inside, it looks like a Big Bang. This means our universe could be inside a black hole in a larger parent universe, and every black hole in our universe might contain its own cosmos, each with its own galaxies, stars, and potentially life. It's turtles all the way down, or rather, universes all the way down. This idea is highly speculative and may be untestable, existing more in the realm of mathematical possibility than observable science. But it's a beautiful thought, isn't it? That creation and destruction might be unified, that black holes might be wombs rather than tombs, that the universe might be far more vast and nested than we can possibly observe. When matter falls toward a black hole, it doesn't fall straight in, it has angular momentum, so it forms a swirling disk called an accretion disk. Friction within the disk heats the matter to millions of degrees, causing it to radiate intensely. For supermassive black holes actively feeding, these accretion disks can outshine all the hundreds of billions of stars in their host galaxies combined. The disk is relatively tiny, perhaps light days or light weeks across, yet from this small region pours forth more light than from a structure 100,000 light-years wide. It's the most efficient power generation mechanism in the universe, converting up to 40% of infalling matter's mass directly into radiation through the extreme physics near the event horizon. By comparison, the Sun converts only about 0.7% of its mass into energy through nuclear fusion. Black holes are better at generating power than stars are, a counterintuitive fact that reveals how powerful gravity becomes when compressed to these extreme densities. Darkness generates light. Falling generates brilliance. The universe's engines of destruction are paradoxically among its brightest sources of illumination. Black hole physics has unexpected connections to deep areas of pure mathematics. The study of black hole thermodynamics connects to number theory, modular forms, and mathematical structures that seem far removed from physics. Researchers have found that the equations governing certain black holes in string theory are related to mathematical objects studied by pure mathematicians for entirely different reasons. This unreasonable effectiveness of mathematics suggests that reality and abstract math are connected in ways we're still uncovering. Black holes serve as bridges between physics and mathematics, their properties described by equations that exist in both physical and purely abstract realms. When physicists study black holes, they sometimes discover new mathematical structures. When mathematicians develop new abstractions, physicists sometimes find they describe black holes. The universe seems to be mathematical at its core, and black holes, extreme, simple, elegant, are where this mathematical nature becomes most apparent. They're not just physical objects but mathematical objects that happen to exist in reality, Platonic forms given gravitational substance. Dark matter makes up about 85% of the matter in the universe, but we don't know what it is. We know it's there because we can see its gravitational effects, but it doesn't emit, absorb, or reflect light. One intriguing proposal is that dark matter might be primordial black holes formed in the early universe rather than from stellar collapse. These could range from asteroid mass to thousands of solar masses, floating through galaxies, their gravity affecting galactic rotation curves and gravitational lensing exactly as dark matter does. They'd be dark because they're black holes, and they'd be matter because they have mass. Recent observations have constrained this theory. Not all dark matter can be primordial black holes, but some fraction might be. It's an elegant idea. We don't need to invent exotic particles to explain dark matter. Perhaps it's just black holes, objects we already understand, sort of, formed in the universe's first moments and wandering through space ever since. The search continues, with astronomers looking for telltale signs that might reveal if dark matter is, at least partially, composed of these ancient gravitational fossils. Because of extreme time dilation, if you positioned yourself near a black hole's event horizon, you'd see the distant universe's time accelerated. What normally takes billions of years would appear to happen in hours or days from your perspective. Stars would be born, evolve, and die in fast forward. Galaxies would merge, restructure, and age. If you stayed there long enough, and impossible. But bear with me, you could watch the universe approach its heat death, stars burning out, black holes evaporating, everything cooling to near absolute zero. You'd be preserved in your bubble of slowed time while the universe aged and ended around you. It's the ultimate isolation and the ultimate viewing platform, cut off from the universe but watching its entire future unfold like a time-lapse film. Of course, you couldn't stay there indefinitely. You need impossible technology to maintain position and survive. But the physics allows it in principle. Black holes offer not just spatial journeys but temporal ones, turning time itself into something navigable, flexible, a dimension you could use to skip forward through cosmic history. Roger Penrose proposed that the universe has a kind of modesty, singularities. Those points where physics breaks down and quantities become infinite are always hidden behind event horizons. This is called the cosmic censorship hypothesis. According to this idea, you can have a naked singularity, a singularity not surrounded by an event horizon, visible to the outside universe. All singularities must be clothed by black holes. This isn't proven, and physicists have found some exotic scenarios where naked singularities might form, but they generally require unrealistic conditions. If cosmic censorship is true, it means the universe protects us from the most extreme breakdowns of physics, keeping them locked away where they can't affect the broader cosmos. It's as if reality has safety mechanisms, ensuring that the regions where our current theories fail are quarantined, unable to influence the universe at large. Whether this is truly a law of nature or just a tendency remains an open question, but it would be a beautiful principle if true, that the universe hides its deepest mysteries behind boundaries we cannot cross. When we finally develop a working theory of quantum gravity, unifying general relativity and quantum mechanics, the best place to test it will likely be black holes. Their event horizons and singularities are where quantum effects and gravitational effects are both strong, where either theory alone suffices. Observations of Hawking radiation, measurements of black hole entropy, studies of information preservation, and perhaps even detection of quantum corrections to event horizons. All of these could provide empirical tests of quantum gravity theories. Black holes are nature's most extreme laboratories, compressing matter and energy to densities where quantum mechanics and gravity must both be taken fully into account. When string theory, loop quantum gravity, or some yet undiscovered theory finally makes testable predictions, those predictions will likely involve black holes. They're the Rosetta Stone for quantum gravity, the phenomena that will let us decode the universe's deepest layer of reality. By studying them, we're working toward the holy grail of physics, a complete, unified description of all forces and particles, valid from the smallest quantum fluctuations to the largest cosmic structures. Certain black holes show quasi-periodic oscillations, flickering patterns in their X-ray emission that repeat regularly, sometimes many times per second. These oscillations likely come from hot spots in the accretion disk orbiting very close to the event horizon, or from instabilities in the flow of matter as it spirals inward. The frequency of these oscillations tells us about the black hole's mass and spin. Faster oscillations generally mean smaller, faster spinning black holes. By studying these cosmic heartbeats, astronomers can probe the region very near the event horizon, testing general relativity in extreme conditions and mapping the geometry of space close to the black hole. Some black holes pulse steadily like metronomes. Others flicker chaotically. Each pattern reveals something about the complex dance of matter and magnetism and gravity happening in the final moments before matter crosses the event horizon. These aren't slow, steady objects but dynamic systems with rhythms and patterns, beating out gravitational songs we're only beginning to learn to interpret. In the far future, After all stars have burned out and galaxies have scattered, supermassive black holes will be among the last structures remaining. They'll persist for 10 to the power of 100 years or more, slowly evaporating through Hawking radiation but outlasting everything else. For most of the universe's future, measured not in billions but in gugals of years, black holes will be the dominant objects, the last remnants of an era when matter clumped together into stars and galaxies. This long epoch, sometimes called the black hole era, will be a time of darkness and patience, where these gravitational giants slowly decrease in mass, occasionally absorbing stray particles but mostly just existing, waiting for quantum processes to gradually dissolve them. It's sobering and peaceful at once. The universe's far future is quiet, dark, and ruled by black holes until even they surrender to the quantum and evaporate into radiation. Everything returns to energy eventually, but black holes take the longest path, persisting through unimaginable timescales before finally releasing their mass back to the void. The sound of two black holes merging, converted from gravitational waves to audio frequencies, sounds like a chirp, a rising tone that sweeps upward in pitch before ending abruptly. As the black holes spiral closer, they orbit faster, creating gravitational waves at higher frequencies. The pitch rises, the amplitude increases, building to a climax as the two black holes touch and merge. Then silence. The merged black hole settles into its final form, perhaps with some brief ringing, as it vibrates like a struck bell before becoming still. Each chirp lasts only a fraction of a second, but it encodes information about the masses, spins, and distance of the black holes. These sounds are among the most profound ever detected. They're not vibrations in air but vibrations in spacetime itself, the fabric of reality rippling from collisions billions of light years away. Listening to these chirps, you're hearing events of unimaginable violence, translated into sound, cosmic catastrophes that release more energy than all visible light in the universe, all happening in silence except for these gravitational echoes we've learned to detect and hear. The supermassive black holes at galaxy centers likely formed through many mergers, smaller black holes colliding and combining over billions of years. Each merger produced gravitational waves, now spreading through the universe. By detecting these waves with current and future gravitational wave observatories, astronomers can reconstruct the merger history of these giants, tracking how they grew from smaller seeds to their current enormous masses. It's like reading a family tree written in space-time ripples, tracing lineages across cosmic time. The gravitational wave background, a constant hum of waves from countless distant mergers, may already surround us, detected recently by pulsar timing arrays. This background is the combined signal of all supermassive black hole mergers throughout the universe's history, a choir of gravitational voices singing the story of how these objects grew and evolved. By listening to this cosmic hum, we're reconstructing history, learning how the universe's largest black holes assembled themselves from smaller pieces, collision by collision, across billions of years. Entropy, usually defined as disorder or the number of possible microscopic states of a system, takes on new meaning with black holes. Black hole entropy is proportional to the event horizon's surface area, and it's enormous. A black hole with the sun's mass has more entropy than the sun itself, even though the sun is a complex, structured object and the black hole is simple. This suggests that entropy isn't just about disorder but about information, specifically, about how much information is needed to fully describe a system. A black hole's entropy reflects the information stored on its event horizon about everything that fell in. This connection between entropy, information, and geometry, surface area, has profound implications for understanding thermodynamics, quantum mechanics, and the nature of information itself. Black holes are teaching us that information is physical, that entropy is geometric, and that the universe keeps meticulous accounts of what happens, even when things disappear behind event horizons. They're bridges between abstract concepts like information and concrete physical quantities like area, revealing deep unities in the fabric of physical law. The study of black holes has been recognized with several Nobel Prizes in physics, testament to their importance. Roger Penrose won in 2020 for his mathematical work proving that black holes are inevitable consequences of general relativity. Reinhard Genzel and Andrea Ghez shared that prize for discovering the supermassive compact object at our galaxy's center. In 2017, Rainer Weiss, Barry Barish, and Kip Thorne won for the detection of gravitational waves from merging black holes through LIGO. These awards recognize not just the discoveries themselves but the decades of patient work, theoretical insight, and technological innovation required to study these invisible objects. Black holes have moved from mathematical curiosities to observed realities, from science fiction to legitimate science, and this transformation has been acknowledged at the highest levels. The universe rewards our curiosity about its most extreme phenomena, and black holes have proven worthy of humanity's most careful attention and most prestigious recognition. As we near the end of our journey, let's reflect on what black holes teach us: that the universe operates on scales and principles far beyond everyday human experience. Time can slow or speed up. Space can curve. Information can be preserved in unexpected ways. Objects can be so massive they create inescapable boundaries in space-time. These aren't science fiction fantasies. They're real features of the cosmos we inhabit. Black holes challenge our intuitions because our intuitions evolved for survival in a narrow range of conditions: moderate gravity, moderate speeds, room temperature. But the universe doesn't care about our intuitions. It follows mathematical laws that produce phenomena stranger than we initially imagined possible. Black holes are humbling reminders that reality is vastly larger, stranger, and more wonderful than the small corner we directly experience. They invite us to expand our thinking, to embrace mystery, to accept that understanding requires letting go of preconceptions and following where evidence and mathematics lead, even into darkness. Some futurists and theoretical physicists speculate that sufficiently advanced civilizations might intentionally create black holes for various purposes, as power sources, using the Penrose process or accretion energy, as ultimate waste disposal, though the information paradox complicates this, as tools for gravitational manipulation, or even as time machines or communication devices. Creating a black hole would require concentrating enormous mass in a small region, far beyond our current capabilities, but not necessarily beyond the capabilities of a highly advanced technological species. Whether such civilizations exist elsewhere in the universe, we don't know, but if they do, black holes might be as much engineering tools as natural phenomena. It's a speculative but fascinating thought, that the black holes we observe might not all be natural, that some could be artifacts of ancient, powerful civilizations, cosmic infrastructure left behind by those who mastered gravity itself. We have no evidence for this, but the universe is vast and old, and the possibility reminds us that the cosmos might contain wonders we haven't yet imagined. Everything in the universe is temporary, even black holes. After unimaginable timescales, they'll evaporate completely through Hawking radiation, leaving behind only a faint haze of particles spreading through space. But their influence persists in other ways. The heavy elements forged in the stars that created them, scattered by supernova explosions, remain in planets and living beings. The gravitational waves they produce during mergers travel forever through the universe. The galaxies they helped shape continue to evolve along paths influenced by their ancient presence. Even after a black hole vanishes, its story continues in its effects on the cosmos around it. Nothing is ever truly gone. Everything transforms, influences, continues in new forms. This is true for black holes as it is for stars, for planets, for living things, for thoughts and actions. The universe is a web of connections and influences, where even the disappearance of its most massive objects leaves ripples that persist. Black holes teach us about impermanence and continuity, endings and transformations, the way everything eventually returns to the cosmic ocean while still leaving its mark on existence. People from every nation, culture, and background look up at the night sky and wonder. Black holes captivate human imagination across all boundaries. They're subjects of scientific papers and science fiction, of documentaries and dreams. When LIGO detected gravitational waves, the news spread worldwide with genuine excitement cutting across linguistic and cultural barriers. When the Event Horizon Telescope revealed the first black hole image, people everywhere shared in the marvel of seeing the unseeable. Black holes remind us that we're all passengers on the same planet, orbiting the same star, living in the same galaxy with a supermassive black hole at its center. They are part of our shared heritage as humans, phenomena that belong to no nation but to everyone who looks upward and asks questions. In contemplating black holes, we're united in wonder, in curiosity, in the desire to understand our place in the cosmos. They're bridges not just between scientific disciplines but between peoples, reminders that some questions transcend our differences and speak to universal human desire to comprehend the universe. Black holes are fascinating because they balance on the edge between known and unknown. We understand them well enough to predict their existence, detect them, measure their properties, and test our theories against observations. Yet profound mysteries remain. What happens at singularities? How is information preserved? Do they connect to other regions of space-time? What's the correct quantum theory of gravity? This combination, understanding enough to ask deep questions but not enough to fully answer them, is what makes black holes perpetually engaging. They're not impenetrable mysteries. We can study them scientifically, nor fully solved puzzles. Deep questions remain. They exist in that sweet spot where human knowledge meets the frontier of ignorance, where we understand enough to glimpse the deeper mysteries that lie beyond. This is where science happens, where curiosity finds fertile ground, where each answer reveals new questions. Black holes will likely fascinate humanity for centuries to come, always yielding new insights while preserving their core mysteries. To study black holes, objects that emit no light themselves, we've had to develop extraordinary technologies. Gravitational wave detectors like LIGO use lasers to measure distortions in space-time smaller than the width of a proton. The Event Horizon Telescope links radio telescopes across the entire Earth, creating a virtual telescope as large as our planet to resolve the tiny angular size of distant black holes. Space-based X-ray observatories detect the high-energy radiation from superheated matter in accretion disks. Supercomputers simulate black hole physics, solving Einstein's equations in scenarios too complex for analytical solutions. These instruments represent human ingenuity at its finest, centuries of accumulated knowledge in physics, engineering, and mathematics, applied to detect and study the universe's most extreme objects. Every observation is a triumph of human capability, proof that patient, collaborative effort can reveal even the most hidden cosmic phenomena. The fact that we hairless apes on a small planet can detect ripples in spacetime from collisions billions of light years away is itself a kind of miracle, a testament to what scientific method and human curiosity can achieve together. General relativity predicts black holes, and observations confirm that black holes exist and behave as the theory predicts. Every gravitational wave detection, every orbital measurement of stars around Sagittarius A, every property of accretion disks, all match Einstein's century-old equations with remarkable precision. Yet black holes also expose where general relativity breaks down, at singularities and when quantum effects become important. They're simultaneously our theory's greatest triumph and the signposts marking its boundaries. This duality is important. science progresses by testing theories until they break, then developing new theories that work where the old ones failed. Black holes are perfect for this. They're extreme enough to push theories to their limits but accessible enough, through indirect observation, that we can actually study them. They're laboratories where we test the edges of human understanding, where we celebrate what we know while clearly seeing what we don't yet know. The universe has given us these natural laboratories, extreme enough to be challenging, observable enough to be useful, teaching us both what works and what needs deeper explanation. The equations describing black holes have an austere beauty that physicists and mathematicians admire. The Schwarzschild solution, describing a non-rotating black hole, can be written concisely in just a few lines. The Kerr solution, adding rotation, is more complex but still remarkably compact considering the sophistication of phenomena it describes. These aren't ugly, patched-together equations with arbitrary constants and special cases. They're elegant mathematical statements that emerge naturally from general relativity's principles. This elegance suggests we're glimpsing something fundamental about the universe's structure. When theories are beautiful, simple, symmetric, mathematically natural, they often turn out to be true. Black holes exemplify this. Their mathematics is so clean, so inevitable given general relativity's axioms, that they almost had to exist. The universe seems to favor elegant solutions, mathematical structures with symmetry and simplicity. Black holes, despite being physically extreme, are mathematically simple, described by equations that feel inevitable, as if the universe couldn't have avoided creating them. In everyday life, darkness is absence. Absence of light, absence of information. But black holes show us that darkness can be rich, complex, full of structure and meaning. A black hole is dark not because nothing is there but because gravity is so strong that light cannot escape. Behind that darkness lie stories. The star that collapsed, the matter that fell in, the geometry of curved spacetime, the quantum information encoded on the event horizon. Darkness here isn't absence but presence so intense it's hidden from view. This is philosophically interesting. What we cannot see can still be profoundly real, perhaps more fundamental than what we can see. The visible universe may be just the surface, with deeper layers hidden in darkness, not empty darkness but darkness full of structure, information, and reality. Black holes teach us to look beyond the visible, to infer the invisible, to trust that mathematics and reason can reveal truths hidden from direct perception. They remind us that reality extends beyond observation, that the universe contains depths we must learn to read indirectly, through their effects and through the shadows they cast. In centuries to come, when historians of science look back at our era, they may identify the study of black holes as one of humanity's most remarkable intellectual accomplishments. We've confirmed the existence of objects predicted by pure thought, objects so extreme they bend time and trap light. We've detected their mergers through gravitational waves, ripples in spacetime itself, proving that spacetime is a physical thing that can vibrate. We've photographed the shadow cast by a black hole 55 million light-years away. We've shown that general relativity, formulated over a century ago, correctly describes the universe's most extreme gravitational environments. These achievements required international collaboration, technological innovation, and deep theoretical work. They represent humanity at its best, curious, patient, cooperative, using reason and observation to understand the cosmos. Future civilizations, looking back, may see this era as when humans first truly grasped the nature of spacetime, gravity, and the extreme objects that the universe creates. We're privileged to live in this time of discovery, to witness as our species unlocks the secrets of black holes. As we approach the end, consider how far we've traveled together. We began with simple facts, what black holes are, how they form, and moved through increasingly sophisticated concepts, time dilation, information paradoxes, gravitational waves, quantum effects, thermodynamics, connections to fundamental physics. You've absorbed ideas that would have seemed impossible to understand at the journey's start. This is how learning works, step by gentle step, each new concept building on the last, until you find yourself understanding things that once seemed incomprehensible. Black holes are complex, yes, but they're not beyond human grasp. You've proven that tonight by staying with me through 100 facts, each one adding to your mental model of these remarkable objects. Whether you remember every detail doesn't matter. What matters is that you've expanded your understanding of the universe, that you've touched, even briefly, some of the deepest mysteries science has uncovered. You've journeyed from the familiar to the extreme and back again, and you've emerged with broader perspective on reality. That's valuable, and you should feel proud of your curiosity and patience. The atoms in your body were forged in stars, and some of those stars ended their lives by collapsing into black holes. The heavier elements, iron in your blood, calcium in your bones, were created in stellar cores and scattered into space by supernova explosions, some of which left black holes behind. You are quite literally made of stardust, and some of those stars are now black holes. Moreover, you exist in a galaxy with a supermassive black hole at its center, an object whose gravity has influenced the galaxy's structure and evolution, indirectly shaping the conditions that allowed our solar system to form and life to emerge. Even more broadly, the gravitational waves from distant black hole mergers are passing through you right now, stretching and squeezing space, and you with it, by imperceptible amounts. You're connected to black holes through history, through composition, through gravity. They're not distant curiosities but part of the cosmic ecosystem that made you possible. In contemplating them, you're learning about your own origins, your place in the universe, the web of connections that links you to the cosmos. Black holes teach us that some of the universe's greatest secrets reveal themselves only to those who watch and wait. Stellar mass black holes were inferred through patient observation of binary star systems, tracking X-ray emissions over years. The supermassive black hole at the Milky Way's center was discovered by tracking stars' orbits for decades, carefully noting positions and velocities year after year. Gravitational waves required decades of technological development and multiple generations of detectors before the first detection in 2015. The Event Horizon Telescope image came after years of coordination, data collection, and processing. None of these discoveries happened quickly or easily. They required sustained effort, careful measurement, and the patience to let nature reveal herself in her own time. This is true for science generally, but especially for black holes, invisible objects whose presence must be inferred, whose properties must be carefully deduced from indirect evidence. The universe doesn't yield its secrets to those who demand immediate answers, but it generously rewards those who observe carefully, think deeply, and persist patiently. Black holes are lessons in the value of sustained attention, reminding us that the deepest understanding comes through commitment to careful, long-term study. Black holes have captured human imagination far beyond physics and astronomy. They appear in countless science fiction stories as mysterious gateways, cosmic dangers, or ultimate unknowns. They've inspired visual art, paintings, and digital creations exploring what these objects might look like, how space-time might appear warped around them. Musicians have composed pieces inspired by gravitational waves, translating the chirps of merging black holes into auditory experiences. Poets write about them as metaphors for loss, mystery, inevitability, or transformation. Philosophers discuss their implications for time, causality, and the nature of reality. This cross-pollination between science and art enriches both. Artists help us imagine and emotionally connect with phenomena beyond everyday experience. Scientists, in turn, are sometimes inspired by artistic visions to ask new questions or see problems from fresh angles. Black holes sit at the intersection of knowledge and imagination, rigorous enough for scientific study yet mysterious enough to spark creative exploration. They belong to everyone, to physicists calculating their properties and to artists exploring their meanings, to anyone who looks at the darkness between stars and wonders what secrets it holds. We've traveled together through 100 facts about black holes, exploring their properties, their mysteries, their connections to fundamental physics and to us. And what have we learned ultimately? That black holes are remarkable not despite their mysteries but because of them. They show us that the universe is comprehensible yet inexhaustible, that each answer leads to deeper questions, that reality extends far beyond the surface we perceive. They teach us humility, our intuitions fail, our theories reach limits, and confidence. We can still study them, learn about them, make real progress in understanding. They demonstrate that the cosmos is stranger than we imagined and that strangeness is cause for wonder, not fear. In black holes, we find darkness that's not empty but full, endings that might be beginnings, simplicity that emerges from complexity, and mysteries that inspire rather than discourage. They remind us that the universe is ongoing, not fully known, still revealing itself to those who ask questions and seek answers. Perhaps most importantly, black holes teach us that it's okay not to have all the answers, that mystery and knowledge can coexist, that the boundary between what we understand and what we don't is where the most exciting discoveries happen. They invite us to remain curious, to keep questioning, to embrace the unknown as an opportunity rather than an obstacle. And so, dear traveler, we've reached the end of our gentle journey through the cosmos's darkest wonders. We've explored black holes from every angle, their birth in dying stars, their role in shaping galaxies, their strange effects on time and space, their connections to the deepest mysteries of physics. We've seen how they challenge our understanding while rewarding our curiosity, how they hide information while preserving it, how they represent both endings and potential beginnings. As you rest now, let these thoughts drift through your mind like stars across the night sky. Black holes are out there in the darkness, patient and eternal, following the laws of gravity and quantum mechanics, slowly evaporating over timescales that dwarf imagination, occasionally merging in unions that send ripples through the very fabric of space. They were there before humans evolved, before Earth formed, and they'll persist long after our sun has gone dark. They're part of the universe's grand architecture, necessary consequences of gravity and matter, elegant solutions to Einstein's equations. You exist in a universe that contains these remarkable objects, and that itself is wondrous. You're made of atoms forged in stars, living on a planet orbiting a star in a galaxy with a supermassive black hole at its center, experiencing time and space shaped by gravity's gentle curves. You're connected to everything, to the stars, to the darkness, to the gravitational symphony playing constantly throughout the cosmos. Even now, gravitational waves from distant black hole mergers are passing through you, through this room, through the planet, stretching and squeezing space-time by amounts too small to feel but large enough to detect with our most sensitive instruments. Let the vastness comfort you rather than overwhelm you. You're part of something large and ancient and ongoing, a universe that creates stars and black holes and galaxies, and somehow, you, consciousness arising to contemplate the cosmos, mind emerging to understand gravity and time, life finding ways to study even the darkest corners of existence. As sleep begins to embrace you, imagine yourself floating peacefully in space, safely distant from any black hole, watching the universe in all its dark and luminous glory. Stars shine with steady light. Galaxies spiral slowly through the darkness. And scattered throughout, invisible but present, black holes exist, not as threats but as teachers, not as endings but as transformations, not as simple darkness but as complexity and mystery waiting patiently to be understood. Rest well, knowing that the universe is vast and strange and beautiful. That black holes, for all their power and mystery, follow comprehensible laws. That human curiosity and patience can illuminate even the darkest phenomena. That the cosmos continues its slow evolution whether we wake or sleep, and that's exactly as it should be. Thank you for drifting through this journey with me. If you found peace or wonder in these cosmic explorations, consider subscribing to continue these tranquil voyages through science and space. Share this with someone who needs calm and curiosity tonight. And know that you're always welcome back to this peaceful corner of the universe, where questions are gentle and mysteries are friends. Sweet dreams, fellow traveler. May your rest be deep and your dreams filled with stars. Good night.